fixed wings, I'm gonna go over, boom, these things. So lift, I don't know, how many of you guys know how lift works? Okay, but could you explain how lift works? Okay, we're gonna go into a bit from the physics so we can actually like get some ideas how it works. And then we have to go over stall and just general airplane stuff. It's a bit also general physics stuff, CG, CP, stuff like that. If it's too easy, tell me, but I do want to go over it this time, and the next time we're going to go a bit more in depth about actual how you make them. Because I've made a lot of airplanes. But yeah, so let's, and then for the next time, there's going to be stability and more like actual niche things and specialities, what we will actually be using. But technically, with the knowledge you will get today, you can make an airplane or out of home. Or if you really want it, out of home. But yeah, and then also next time we're going to go over the manufacturing things again. So yeah. But it all starts off with Bernoulli, also Newton, but Bernoulli and the Newton, I don't even want to fucking talk about it because we should all have a general understanding about it. But Bernoulli, I don't know, I hope, have you had Bernoulli equation before? No? Okay. Kind of the point is, you have this equation, which is pressure, and then you have like the energy parts. It's just basically an energy equation. So both sides are equal, or it's a constant. So if we'll change one parameter, one will change. Based on this, we will take a look. Airfoils are born. So yeah, this is in a pipe. It's a simplified version of it, so you can kind of understand about it. But you can see that the velocity actually changes, and pressure changes because of it. It's what we have right here is it's a Venturi tunnel. It's called sometimes that. Just a little bit of a restriction in the tube. It will drop the pressure actually, and you can use it for all kinds of reasons. Usually Venturis are used in carburetors to get gasoline to atomize in air. So if you would imagine you have a little hole there which feeds gasoline, you could get the ongoing air to just atomize the gasoline and then burn that mixture. But yeah, it's basically that. It's a kinetic and a potential energy. You don't really look at potential energy, especially if you're talking about airplanes and stuff like that. But the point is, kind of, you just look at the pressure. If you have pressure, the higher the pressure, the lower the velocity. Or no, opposite. Let's take a look at it. Okay, let's say it's a constant, right? So you could write it like, boom, you have the kinematic one, and then you say that that's a constant. Right? Yes. Because we're not looking at the potential, and both sides have to be the same. It's just this is the simplest way of like taking a look at it. You have the least amount of stuff going on. So let's say we increase the velocity. If we increase the velocity, then pressure has to drop because the thing is constant. Exactly the same in the opposite way. Now from this, we can actually take a look at how airfoils work and start thinking about, well, if we have moving fluids or air, how can we get something to lift up just from ongoing air? Let's say you have this at the start, and you have streamlines, whatever. But this is there, and it's moving around, right? now nothing really happens. There's just some accumulation of pressure here and some less pressure here. Doesn't matter. Point is, when you do this magical shape and we change, we basically have what do you call it? In English it doesn't really work. Like you don't have triangle, quadrangle, that stuff. But if you would have a biangle or a shape with two edges, then you have smaller path here and higher path here. Now, whenever people are going to explain wings, the truth is there's no one single classical physics explanation that works perfectly, because you get holes in each and every one of them. But these are the two general explanations which are the most respected. If you have the two sides of the wing, this is called, is a leading edge, is the front leading part of the wing, or of the airfoil, and then this part is the trailing edge. Now here you're going to have a lot larger of a distance that the molecules have to travel. Boom, 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 boom. And what you actually see is, if it's going to be traveling through air, they actually have very similar times. Let's say that you have two molecules, or two air particles, whatever, and they go through the whole path. They are actually very close to each other after they did the whole path. Now this tells you two things. First of all, because these distances are different, the velocity of the particles were different. And because of that, if you know that you had higher velocity on the top, you get lower pressure, which is, I don't know, P low, and then P high. Now what happens if you have two different pressures and something in between? Okay, forces. You get force. So you get a force that goes from the low, from the high to the low, and we call this lift. So that's kind of how airfoils work. Now, no airfoil looks like that. Not anymore. Back in the day, they actually did. Why? Because a lot of aerodynamical reasons, but mostly it's this point is very unstable and it can change the trajectory of the whole wing quite quickly. So you make it blunt. If you make it blunt, the molecules aren't like, whoa, whoa, where am I going to go? If they were like, okay, I'm going to go this way. They're not really like, you're not really cutting with a sharp knife through the tomato and messing up the cut really badly. You're more like bluntly squishing the tomato in half. But yeah, so that is the first explanation, is the pressure one. And then actually, if you take a look at it, you do have a little bit of a mismatch of the molecules over. And there's another thing, it basically makes it that if you look at the downwash from the wing, that's why it's called the downwash, you get a little bit of the air going a little bit down. Now I'm exaggerating it here, but because of that, you could take Newton's formula and say that you are giving the molecules an acceleration down, so in turn you're going to get acceleration up. I.e., you get the force up, you get lift. Yeah, so that's kind of how that stuff works. And now let's go and talk about the forces and the angles and the names that we use quite a lot. So as you can see, if you draw a line from the leading edge to the trailing edge, a straight line, that's called a chord line. You will meet this quite a lot when looking at airfoils, when looking at how do you actually In this case, it would be plus or minus 0. And then you take a look at some of the forces. Now, this whole thing, this whole action, it takes work, and we don't get any work for free. So we will get drag, which will be, you have thrust that way, so you will get drag this way. An ideal airfoil is depending on the use case, and there are airfoils that are specifically ideal for lift. So they have what we call this a lift to drag. Oh, it's usually, yeah, I think it's a lift to drag ratio. And usually this number is quite a bit higher than 1. If you have it lower than 1, you're doing something really bad. So you get a lot more force in lift than you get in drag. That's why the airfoils are actually used. That's where we're not flying always on with helicopters, with airplanes, which makes more sense. You can carry way more for a lot less power. Yeah, and then you get the resultant force, which is the actual force that you get if you would, like, I don't know, take a look at the pressures, you do the freaking, all the tiny things. Well, it would be kind of higher here, and then a bit smaller ones here for pressures. So you would get the pressures, and you count them up, blah, 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 blah. But, yeah, you get the resultant force. Point is, don't really care about it. You really care about what's your lift, what's your drag. And lift and drag, as you can see, it just depends on the angle of attack, because if you change the angle of attack, the resultant force will, like, the angles will change. Another thing is that lift and drag will always be relative to the horizon and not to the airfoil itself. It's just how you define lift and drag. Yeah, and now let's talk a little bit about these things that NASA wants to talk about. So if you make angle of attack, if you make it so the air comes a little bit from beneath, you actually also have more deflection, and because of Newton, you're gonna get more lift. And you get quite a bit more lift. Now you can see that it's almost linear, and at some point you lose it. This is because you get what we call separation. Usually over the wing you get nice, smooth laminar flow. Let's not get into what's laminar flow versus turbulent flow. Okay, let's get into it a little bit. Point is, laminar flow is smooth. Turbulent flow is chaotic. You don't know where it's gonna go. It's like all kinds of crazy movement. Now, if you will increase the angle of attack, you will get some of the molecules not being able to be sucked onto the surface of the thing anymore. So at some point, you will get it to go away from the surface. And this region will be filled in with kind of static stuff. And it's like little eddy currents, little pockets of air just doing random stuff chaotically. So effectively you change the actual profile of the air moving around just by changing the angle of that. This is what we call air separation, I think, yeah. Flow separation, sorry. Flow separation, and you have like a point of where it separates and so on and so forth. But the thing really that is very, 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 very acute for airplanes is that you can notice it. You get a change of pressure on the wing itself. So you could have special things that can monitor the pressure on different places of the wing to notice that, oh, we're getting some separation. You might have seen videos on YouTube of little strings on the wings, and they get all chaotic. That means that there's air separation going on, and you get all kinds of currents there moving around. And when that happens, you effectively lose all reasonable lift. So it goes from you're gaining lift to freaking nothing. Yeah, it's attached. Attached flow. When it's stalled, you get the separation. Now, that's how stall works. But let's talk about airplanes. So, first of all, you can see that there are blacked out parts, and then there are the parts that are just yellow. No, it's orange. It's crazy yellow for me. Point being, the orange parts, those are the parts that are not moving. The black parts usually move. And the moving parts we call control surfaces. Because you can control that surface, you can change the behavior of the air around it. Now, let's go over some stuff. I think I'm going to do it. Now. So if you want to make an airplane, you don't need much. Like this works. So let's say we'll just make a wing. But this is not enough. If you have just a wing, it doesn't generate any control over the thing and so on and so forth. So you have the black on top. Okay, I'm gonna move back to that a bit later because I realized CG and CP I still work on and talk with you guys. But yeah, these are the basic parts of the airplane. So you have the wing itself, the main wing, which is actually generating most of the lift, not most, but all of the lift pretty much. And then you have the little control surfaces. I'll explain why they are in the back. They have a very good reason for being in the back. And then you have all the control surfaces. Now, depending on the control surface and where it's placed, you can induce different behaviors on the airplane itself. So you have special names for them. The back parts of the airplane is always called stabilizers. The one that is horizontal to horizon, or parallel to horizon, or just horizontal, that is the horizontal stabilizer, and then you have the vertical stabilizer for controlling yaw and stuff. And then the control surface, only the control surface of the horizontal stabilizer is called an elevator. Just like that, you also have it for the vertical stabilizer. The vertical stabilizer's control surface is called the rudder. And then you also have the rolling action of the airplane itself. And those are controlled with, on the wings, you have control surfaces. Those are called ailerons. Yes, ailerons. Now, you can actually mix and match if you have special airplane types, because these control surfaces, these three main ones, elevator, rudder, and ailerons, are kind of tied to what dimension do they change on the airplane itself. Elevator always changes the pitch. Rudder always changes the yaw. And ailerons always change their role. If you have some special geometry of your aircraft, you might have special names for those control surfaces. Now let's talk about some special entities. The control surfaces usually are mounted behind the wing, like here. And what they do is they move up and they move down. So if it moves a bit down, it actually increases the drag and increases the lift. If it moves up, usually still increases the drag and decreases the lift. By changing that, you can do the controls. But what I wanted to show you in particular is you can also change the geometry of the wing in many different areas. You can see on most airplanes nowadays, bigger ones, you also have slats. They are in front. This usually extends the wing's length, which also increases the lift, but increases the drag. So for takeoffs and landings, we would use them, but not in cruise. Then you can also have something amazing, which is called a spoiler. It depends on how you build them, but usually it's just a wall that just extends from the wing and totally disturbs all airflow around it, makes crazy airflow all around, and you lose a lot of lift and increase drag drastically. Which one? There is no.
There should be two buttons you press them at the same time when it goes up.
No. Okay. Oh, colors. Yeah, I'll color in the control surfaces. I'll color in the slats. The air brakes, or sometimes called the spoilers. And then the back one. I hope. Is it kind of clear? Okie dokie. Yeah, it's getting a bit messy. I'll start by okay. So those are the control surfaces of the wing. You can also see in the middle of it, there's flaps. Flaps are always used just to increase lift. They also increase drag, but whatever. They're always used to also just increase lift. Now, flaps and ailerons and all the other control surfaces that are like basic ones that are on the back, they look kind of the same. And but usually flaps are more inwards of the wing, and the other control surfaces are more outwards. I will explain that probably a bit later, why is that the case. But yeah. Did I forget anything from this picture? Well, you get the engine, the fuselage. Yeah, that's one part. The middle part is always the fuselage. It's just there for structural reasons. And the tail you call the tail. I think that's kind of self-explanatory. The cockpit is there because there's like a bunch of chickens and cocks there. No, I'm with you. And what else? I think that's kind of fun. Okay, center of gravity and lift. CG, do you have any idea about it? Some has some idea about it. Okay. Well, center of gravity is basically when you sum up the masses, when you get the G as well, get the M times G. When you sum up all of those little fucking, damn, they'll have to blur the gravity forces, that's the center of gravity. So you have it, I don't know, 2D. This is going to be great. So this is not a wing, this is just a ring. So for a rectangle, it's just in the middle. That's going to be your center of mass. So where's your center of gravity? Well, it doesn't matter because gravity is just on one of the dimensions, so it's going to be right in the middle. That's your CG. For CG, you also have this beautiful drawing that you use. If it's yellow, it's CG. If it's blue, it's usually center of pressure. Sometimes also center of lift. Don't get into it too hard, but point is, when you sum up all the forces, you get the one place where it all balances out. That's the center of it. So you have center of gravity, and you also have center of lift. Usually, if you want to get stable flight, you will have center of lift right around where center of gravity is. But however, you have multiple wings on the airplane itself. You have the main wing, and then you have the control surfaces. They sum up, and you want, for a stable, coordinated flight, to just all of them being in the same spot. So those are the centers. Now, the cool thing that you can do with this is you can make a rocket. No. But what you can do is, where's some white chalk? Okay, let's imagine this brick flying through the air. It's gonna get very unstable. Because depending on what angle, just flying through there. Because depending on the angle, you will get different forces acting on the brick. Now, you can change that by changing the shape of it. Let's not even do the tip, but we can maybe internally, let's add fins. So we're adding little fins. Jig. So center of pressure is basically, if you take a look at the geometrical shape, where is all of the surface? If CG was right in the middle, let's say that the fins weigh nothing. The center of pressure, and I'll redraw the CG into white. The center of pressure is going to be a little bit behind, because you can see that there is definitely more surface on the left side than on the right side. Now you won't be able to differentiate them. Wow. So that's your center of pressure. CP. So if your center of gravity is in front of the center of pressure, it means one thing. Whatever way you're going to move, not always, because sometimes it depends on the geometry, or it doesn't matter, but it's like a dart. So whatever way it will move, the thing itself will correct itself to follow the center of gravity. And because the center of pressure is behind, it will correct itself in the way of center of gravity going right into the wind and center of pressure following it. So that's the basic way of how to get anything to be stable in any kind of way. For airplanes, it's going to be a bit more, but I think we're going to talk about it next time. We're going to talk about more control stuff. Kerbal Space Program. Yeah, here they have the center of lift in front, because then it's easier to actually very, very important measurements. And then when you take into account the fact that you have oopsies, thrust as well, thrust you always want to go straight through the center of mass. If not, it will induce moments on the airplane, and you will have to correct for them. Different wing configurations, you can have low wing, mid wing, high wing, inverted wing, gull wing, dihedral wing, ahedral wing, I think. Yeah, and hedral wing. We will talk about this a bit later because the wing configurations do change your characteristics on the flight. But I think for the filming people, it's going to be, yeah. Different wing geometries, you can make all of them work. You can make the foam board work, fly fine. We actually have a few foam boards we can make it fly. But yeah, usually anything works just fine as long as everything around it is correctly set up. So you can make any wing shape work as long as everything around it is made for also that. Now the sweep of the wing changes. It's called, it changes the controllability of the wing itself, of the airplane. So usually, if they are straight, perfect. If they're swept back, it's usually because of high speeds, and then all kinds of effects. But it's way too complicated for this. Thrust configurations, you're gonna have the motor in front or the propeller. It's gonna be, tractor, we call it a puller usually, or a pusher if it's in the back. On RC models and then drones and so on and so forth, it's usually, you choose this depending on what are you carrying, where do you want the weight, because motors are quite often one of the main components of the weight. And you put the motor where you can while not disturbing the other parts of the airplane. Multi-engines, you get moments if you have one engine working and the other not, and you get moments also from the rotation of the props. There's a bunch of tail types already written down. You can probably figure out there's infinite amount of them, but the conventional one works fine. It's the most easiest one to produce in big scales, but actually for drones, quite often the detail is easier to make, or quite often there's also multiple tails, so you go quite often with like wall mounted and A wing designs. The farther away the tail is from the CG, the more you get of a moment while using less force. And so you can actually make it smaller. Let's say if the airplane is super long, you actually need the surface, the control surfaces to be very, not control surfaces, you need the stabilization surfaces to be very small, stabilizers. The shorter you make it, the bigger you need it. And we're gonna do that next, but we're gonna, it's called the tail volume. And you can calculate it, here's some of the calculations. Usually for the same amount of control, you need the same amount of tail volume. And you can see if you have a crazy heavy fuselage, you might not want to make it too long. And you just make it shorter, just make the stabilizers bigger, and it will work out. Delta wings are usually all triangle type of wings. You have canards for not having, if you don't have the pitch, now I forgot what it was named. The horizontal stabilizer can be in the front, in the back. In the back, it's going to be passively stable. In the front, now you're shifting the center of pressure weirdly. you can control for it, and that's why a lot of fighter jets are actually running canards, not pitch stable, horizontal stabilizers in the back, because you can actually get more control authority out of them. And then you have the tailed ones. Same goes for the rudder. The rudder usually nobody really uses, so it's kind of always in the back. Yeah. Most of the airplanes are monoplanes. But back in the day, because it was very expensive, not expensive, it was impossible with the materials that we had to make more surface. You would get a lot of biplanes, triplanes, and so on and so forth. What I'm saying here is you could technically mount 10 wings on an airplane if you calculate everything right. It will fly. It can be controllable. Yeah, that is kind of done for the theory part.